أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم. Uh, Start with the name of Allah, the most merciful and mighty. Today we will be talking about the chapter infrared spectroscopy. These are the content of our presentation. Introduction, the vibrating diatomic rotor, simple harmonic oscillator, the inharmonic oscillator, and the diatomic vibrating rotator. At okay, chemical bonds exhibit elasticity, causing molecules to deviate from the fixed position under various external forces such as rotation and vibration. In a diatomic molecule, which consists of two atoms, when the only motion is vibration, the atoms oscillate about a mean position. Vibration results in changes in the bond length, leading to the stretching and compression of the bond. Vibrational spectroscopy involves studying the energy levels and transitions associated with the molecular vibrations. When a diatomic molecule vibrates, it absorbs or emits energy in discrete amounts, leading to vibrational spectrum. In a practical scenario, diatomic molecules can undergo both vibrations and rotations simultaneously. The combination of these motions leads to more complex spectra in spectroscopic analysis. In such cases, uh, in such cases, the vibrational and rotational energies are coupled, resulting in hybrid energy levels and selection rules for transitions. Complex molecules exhibit more diverse spectra, reflecting the uh, intercases of their motion. So, first of all, we are going to discuss the vibrating diatomic molecule. Uh, a diatomic molecule is composed of two atoms. So, if we consider an HCl molecule, for example, it experiences two types of motions. Uh, there is repulsion between the uh, positive uh, positive charges that are present in the center of the atoms of hydrogen and fluorine, and between the two electronic clouds. And there is attractive forces between the protons of the respective atoms and the electronic cloud of the respective atoms. So the molecules tend to tend uh, to tend to be at a position where the repulsive forces are balanced by the attractive forces. Uh, this the distance at which the atoms balance their forces, the attractive and the repulsive forces, is called the equilibrium bond distance, or the bond length. Any attempt to distort the bond length requires an input of energy, and we may plot energy against the internuclear distance as shown in the figure 3.1, which is we are going to discuss in our next slide, where we have anchored the chlorine atom on one axis and imagine pushing and pulling the hydrogen atoms closer to or further from the chlorine. uh, a bigger push or a pull results in the rise of the energy. At the energy minimum, the internuclear distance is referred to as the equilibrium distance, or more simply as the bond length. So if we look at this diagram, this is this one. This is the equilibrium bond distance. Equilibrium bond distance is the distance at which the energy of the molecule, the energy of the bond is at minimum distance. So if we take the example of hydrogen fluoride, this is chlorine which is anchored at the y-axis, and we imagine that we push the hydrogen atom. Uh, when it is in compressed form, it is represented by H prime, and when it is in extended form, it is represented by H double prime. E1 represents a lower energy, while E2 represents a lower energy, while E1 represents a higher energy or higher potential. The compression and extension of a bond may be linked to the behavior of a spring, and we may extend the analogy by assuming that the bond acts like a spring which obeys the Hooke's law, which is written as F is equal to minus K R minus R equilibrium. F is called the restoring force. K is the force constant or the strength of the bond, and R equilibrium is the internuclear distance at which the molecule experiences the least energy. In the case of in this case, when we consider the molecule just like a spring, uh, and in this case the energy curve is parabolic, and it has the form E is equal to half K R minus R equilibrium square. The model of vibrating diatomic molecule, the so-called simple harmonic oscillator model, while only an approximation, forms an excellent starting point for discussion of vibrational spectra. Uh, Figure 3.1, as I have already uh, shown you, represents the high energy plot uh, represents the energy plot as a parabola with the minimum energy E naught occurring at the equilibrium distance between the two atoms in the diatomic molecule. Any deviation from the equilibrium distance leads to an increase in the energy due to extension or compression of the bond. If we consider an atom that is chlorine, for example chlorine, to be stationary at the origin R is equal to 0, the other atom, for example hydrogen, will oscillate between its minimum distance h and the maximum distance h prime and the maximum distance h double prime during vibration. In the case of HCl, it is a good approximation to assume that the much lighter hydrogen atoms move during the vibration, while the heavy chlorine atom stays virtually still. However, for any diatomic molecule, we can always imagine ourselves to be sitting on one atom and watching the other atom to move. From this point of view, the atom we are on appears stationary and can be considered fixed on the R is equal to 0 axis. Therefore, diagram like figure 3.1 are applicable to any diatomic molecule where one atom is virtually stationary while the other atom undergoes vibration around the equilibrium distance. Vibrational frequency of a diatomic molecule such as HCl, shown in figure 3.1, remains constant, constant despite changes in the energy. Increasing the energy to E1 leads to more vigorous oscillation with greater compression and extension, but the frequency remains the same. This frequency is called the oscillation frequency. The oscillation frequency of an elastic bond, uh, analogous to a spring, is dependent upon the mass of the system and the force constant, but is independent of the amplitude of the or the amount of distortion. The classical expression for the vibrational frequency omega of a diatomic molecule is given by the equation below, that is omega OSC is equal to 1 over 2 pi under root k divided by mu. If we want to describe the equation in spectroscopic term, we will divide the previous equation by c, that is the speed of light. So uh, the it will be converted into spectroscopic terms, that is centimeter inverse. And we and omega OSC is now represented by omega bar OSC 1 or 2 pi c under root k divided by mu centimeter inverse. Vibrational energy, like all other molecular energies, are quantized. As we all know that rotational energy, vibrational energy, or electronic energy all are quantized, and the allowed vibrational energies for any particular system that is calculated from the Schrodinger wave equation for simple harmonic oscillator is given by EV is equal to V plus 1 over 2 H omega OSC in terms of joules. Here, the value of V can take the values from 0, 1, 2, 3, and so on. Where V is called the vibrational quantum number. If we want to convert it into spectroscopic units, that is centimeter inverse, we will have to divide the energy which is given in joules by Hc, and we will get V plus 1 over 2 omega bar OSC. As the only energies allowed to simple harmonic vibrator, some of these are shown in figure 3.2. So you can see there in the plot that if we put V is equal to 0 in our previous equation, we get a value which is equal to 1 or 2 omega bar OSC. If we put V is equal to 2, we get 3 by 2 omega bar OSC. And there is a constant difference between each successive energy, successive state, that is V is equal to 0, V is equal to 1, V is equal to 2. That is each successive vibrational state, that is equal to omega bar OSC. We should notice that the lowest vibrational energy obtained by putting V is equal to 0 in equation 3.5 or 3.6 is half H omega OSC in joules, and E naught is equal to 1 over 2 omega bar OSC centimeter inverse. This implication is that the diatomic molecule, and indeed any molecule, can never have a zero vibrational energy. The atoms can never be completely at rest relative to each other. The quantity in above equations are known as zero-point energy. It depends only on the classical vibrational frequency and hence the strength of the chemical bond and the diatomic and the atomic masses. Thank you very much.